Hello friends, welcome to Civil Master. In today's video, I am going to discuss about the numerical problems related to shear force diagram and bending moment diagram of different beams. So let's get. So guys, as you can see here, this is our problem. This is the simply supported beam. Its points A and B has supports and have the reactions RA and RB respectively. It carries the uniformly distributed load of 10 kN per meter at the span of 6 meter and 5 kN point loads with at the span far apart from 2 meter from both of the supports, and the total span is of 10 meter. So first of all we have to find out the both of the reactions. So it is RA plus RB is equal to 5 plus 5 plus 10 into 6, which is a UDL. So it is 10 plus 60 is equal to 70 kilonewton. This is our total reaction. Now we have to find out these reactions separately. So let's take the moment at point A so that we can find out the reaction RB. So let's taking moment at point A. So RA into 0 plus RB into 10 as the B point is 10 meter apart from the A point. So RB into 10. Now the upcoming loads and upcoming loads we are taking with negative sign. So 5 into 2 meter minus 5 into 6 plus 2, 8 meter, and minus 10 into 6, and the perpendicular distance will be from the CG of this UDL to the point A, which is 10 into 6 into half of the 6 is 3 plus 2, that is 5, and equal to 0. So let's calculate the value of RB. RB into 10, it is equal to 6 into 5, 30, 30 into 10, 300 plus 8 into 5 plus 5 into 2, it is 40 plus 10, it is 350. So RB is equal to 350 upon 10, that is 35 kilonewton, and similarly RA is also 35 kilonewton as the beam is symmetrical and total load is 70. So the half that load will be distributed to both of the reactions. So now we have all the forces acting on the beam. So let's find out the shear force diagram. First of all, we have to draw the reference lines from all the forces, and this is 5 kilonewton force, this is also 5 kilonewton force. Okay, now let's start from the point. You can start from any from these 2 points. In this question I am starting from the point B. So at the point B we have the reaction RB, and the value of RB is 35 kilonewton. So it will rise up to 35, and from this point to this point there is no any forces, so it will go straight, and at point D it bears 5 kilonewton force, and it is downward force, so it will get reduced from it. So shear force at point D is equal to 35 minus 5, it is 30. So it get reduced by 5, it is 30 at this point. Now there is a UDL acting at 6 meter span from D point to C point. So the shear force diagram will go linearly, and shear force at point C will be 30 minus 10 into 6. It is equal to 30 minus 60. This is minus 30. So it will meet at this point by this. Okay, this is 30. Now at this point, this point has also a force of 5 kilonewton, and so here we have minus 30 minus 5, so it is minus 35. It get reduced by 5 more, and this point is 35. Now from this point to this point there is no any force, so it will go straight, and at this point it is a point A and has a reaction of RA, and the value of RA is 35. So minus 35 plus 35, because this is the upward force and we are taking upward force as a positive, so it is becoming 0. It will now reduce to 0, 35. So this portion is in positive and this is in negative. So guys, now let's draw the bending moment diagram of this beam BMD. And first we have to take the sign conventions. So we will take the clockwise forces as a positive and anti-clockwise forces as a negative. So this is our sign convention, and we will follow this convention and the calculation of bending moment. So let's get started. Now, as you all know that the bending moment at the supports is 0, so bending moment at A and bending moment at point B is equal to 0. So there is no need to find out these the bending moment at point A and B separately. So let's find out the bending moment at point D. So bending moment at point D, it is equal to, you can you either take the bending moment values either from the left to right or from the right to left. So as you can see here, from right to left, as we go from right to left, so we have less values of forces, so it will become easier to find out the bending moment from left to right at point D. So let's take bending moment at D. It is now we are taking the bending moment at point D, and this force is trying to rotate this point in anti-clockwise direction, as you can see here. Yes, so RB is trying to rotate this point at anti-clockwise direction, so we will take this load as a negative load. So minus RB into 2, it is value of RB we have 35 into 2, it is negative, so it is minus 70 kilonewton meter. So it will go below the reference line and linearly, because there is no any force between this and this point, and this is a point load. So it will go downwards by 70, like this. 70, 0. Now let's take the value of bending moment at point C. Now we are also going from left to right. So it is RB, and RB is also rotating this point C in anti-clockwise direction, so we will take it as a negative force into distance from C point to RB is 6 plus 2, it is 8 meter. And now this force is trying to rotate C point as a clockwise, so we will take it as a positive. So 5 into 6, because this direction is 6 meter. And now the UDL, which is also rotating this point as a clockwise, so it is also positive. So it is 10 into 6 into 3, because the center of the UDL is from 3 meter apart from the point C. It is 3 meter. It is RB, which is 35 minus 35 into 8 plus 6 into 5, 30 plus 30, 10 into 6 into 3, it is 180. So minus 35 into 8 plus 30 plus 180, it is minus 70. And as we can see here, this value is also minus 70, but the UDL acting on this span, so this bending moment diagram will go like parabolically. So it is like this, and from this point it will also go to linearly straight up to point 0. Guys, this is the assumed diagram, because we have to find out the exact position of bending moment where the maximum bending moment exists, and which would be found by the this point of contraflexure, where shear force diagram changing their sign from positive to negative. So let's find out the point of contraflexure, and at that point the bending moment will be maximum, and the maximum value of bending moment we will get from that point. So as you can see here, the beam is symmetrical, and the UDL acting on this 6 meter span is also symmetrical. So it is clearly seen that the distance from this point to here and here will get half distributed, so 3 meter and 3 meter. But I'm going to calculate this value of distance of UDL to find the point of contraflexure. So as we know that this is the similar triangle, and this complete span is 6 meter. It is 30, and it is also 30. As you can see here, 30 and 30. So let's take this point as x, and this will become 6 minus x. So according to the theory of similar triangles, 30 upon 6 minus x is equal to 30 upon x. So there's 30x equal to 180 minus 30x. So it is 60x is equal to 180, x is equal to 3. So here we have the distance of point of contraflexure. It is 3 meter from this point. Now we will take moment at the center of this point, at the point of contraflexure. Let's say this point is O, and taking moment at point O. So MO is equal to minus RB into 2 plus 3, it is 5, plus 5 into 3 and plus 10 into 3 into 3 by 2, because UDL is acting on this complete span, but we have to take the moment at this point, so we have to take the distance from until this, and the center of this point from this UDL is 1.5. So here we have minus 35 plus 5 plus 15 plus 5, 8 is 9, 45. So here we have the value of minus 70 plus 15 plus 45. It is 175. So here we have the value of bending moment at point O. It is minus 175 plus 60, it is minus 115 kilonewton meter. So now we will draw the actual diagram of bending moment here. It is coming at the minus 115. So it will go downwards. This is wrong diagram, and the actual diagram will go like this, and this is the maximum bending moment point. Maximum bending moment is 115 kilonewton meter. Thank you guys for watching.